Good evening, everyone. Am I audible? May I know if I'm audible?
Yes, sir.
So we'll get started. Listen. So, what were the previous concepts we discussed? You remember last class I showed you a video trying to explain how surface tension actually works. You remember that? That visiting card kept on top of water and then you drop a liquid solution into that, then the boat will start moving. The visiting card will start moving. So I told you that it is happening because of the breakage of something, some property of a liquid called as surface tension. Right. So having said that, you see, now we'll see what is the definition of this surface tension. Okay. So the thing is, you can write it down. So surface tension is basically the property by which the free surface of the liquid, when I talk this about, when I take this to be the liquid, right? The top surface is there, no? That is called as the surface. So what do you mean by free surfaces? The surface which is exposed to atmosphere or the surface which is exposed to air is what is called as a free surface. So when you talk about the free surface which is exposed to the air, the property by virtue of which the free surface of the liquid at rest starts behaving like an elastic stretched membrane, right? So it is going to behave like an elastic stretched membrane tending to contract so as to occupy the minimum surface area. So the property of the free surface, right? It is the property of the free surface where the free surface tends to behave like an elastic stretched membrane and it is tending to contract so as to occupy minimum surface area. So if you talk about this property, then that is called as surface tension. Okay, this is the first point you need to make a note of. Write it down. So you're able to understand? Now listen. So if you're able to look at the diagram that is there given here, there is a liquid on top of which there is a small needle that is placed. The length of the needle is, let's say it is L. And for that needle, when the distance between A and B is going to be taken as L, there will be a force that is exerted by the liquid surface in both the directions, where it is observed that the force is directly proportional to the length of that particular solid which is in contact with it. Okay. So the force that is being applied on that particular solid, that is the needle, is directly proportional to the length of it. So from here, if I remove the proportionality symbol, then the constant that I'm going to introduce is small t, where that small t is what is, I'm going to introduce this t, where the t is what is called as surface tension. Okay, this t is what is called as surface tension. So from here, I can write t is equal to F divided by L, and surface tension, the SI unit for surface tension is going to be Newton per meter. So the SI unit of surface tension is going to be Newton per meter. Right. Next. So this molecular theory is something which I explained it in the previous class itself. So this was done in the previous class. So the next concept that we'll see is something called as surface energy. Right. Because when I say that the liquid membrane has a tendency to behave like an elastic stretched membrane, the liquid surface, the free surface is having the tendency to behave like an elastic stretched membrane, it is going to have some energy associated with it, right? So that energy, the energy that is possessed by the molecules of the surface film. So when I say surface film, right, let us assume there is something like this. There is a frame like this. Okay. And this frame is covered with the help of a thread. Okay, there is a small plastic frame where you tied a thread, where the thread has the tendency to move. That thread will be able to move, but that C shape will not be able to move. Now, what will happen if I take this kind of a frame, dip it into soap solution and take it out? So when I dip it into a soap solution and take it out, what do you think is expected? So you'll be able to see a soap film that is formed inside. Right? There will be a soap film that is formed inside. Right? So when you look at the soap film, right, what it will try to do is it will start applying the surface tension on the thread and it start pulling itself inside, because what is the property of surface tension? The surface tension will ensure that the liquid surface occupies minimum surface area. So if the area has to decrease, then the surface tension will start acting in this direction. So let me call it as T. And according to the diagram, what the meaning is? Initially, this thread was at point A dash, it was at point AB. And now what we are going to do is, I'll explain the diagram. Now what we are trying to do is, since the film is trying to pull the thread to the left-hand side, we will apply a force on it in the right-hand side and ensure that it has got displaced through a distance of X. Okay. Where I will call this force as, listen to this carefully. We know that surface tension is equal to F divided by L. So can I write it as F is equal to, listen to this carefully, can I write it as F is equal to T into L? So the force that we need to apply is going to be surface tension multiplied with the length of that wire, which is being put, right? Yes or no? I asked a question. Is it yes or no? Okay, I'm giving you all 1 minute time. Everybody please switch on your video, or else I'll just like that remove you from the class. Switch on the videos, please. Chitesh, Aravinda, yes. Others, Eric, Kavya, Kirtana, Mridula, Nivedita, Raghav, KS, Ritika, and Rohit. I want you all to switch on the video. See, those who are not switching it on, those who are not responding will be just like that, put in the waiting room. Then don't ask me. Kavya, Nivedita, Raghav. Good. Yes. So Rohit, yes, I'm able to see Amrisha, Kirtana, Mridula. Kavya, I'm calling you for the last time. Are you there? Okay. I think this will be better now. We can at least have good discussion. Okay, listen. So my question is, did you all understand what I mentioned, what I spoke till now? Nivedita, are you clear?
Yes, sir.
Okay. So what did I say surface tension is? It is a property of a liquid due to which the surface will start behaving like a elastic stretched membrane. And what will it try to do? I gave you in the definition. What is it? It will try to occupy what surface area? Minimum or maximum surface area? It's not this definition. Okay. Don't copy this. Okay. Till I tell you, don't copy this definition. I'll explain and then you can make a note of it. But my question is, in the surface tension part, right? It is trying to occupy, I gave you, tending to contract so as to occupy minimum surface area. So the surface tension has the property of, the surface tension is a property of the liquid which will try to reduce the area. It will try to occupy minimum area because I told you, due to the molecular theory of surface tension, what will happen? Which particle out of A, B, and C will have the which particle out of A, B, and C will have the highest energy? This I discussed in the previous class. Anybody can answer. I'm not asking her alone.
At the top.
Yes, Amrisha, please switch on your video. Yeah, it is at the top. Why is it so? This also I explained it. Why is it? Why is it having higher energy at the top? Aravinda, why is it having a highest energy at the top?
Sir, I can't hear you properly, sir. I have two headphones. So can you please give me a minute?
You reconnected it? Okay, listen to me. I'm asking out of the particle A, B, and C available here, which one has the highest energy?
No, sir, I'm saying I can't hear you properly. So if you give me a minute, I can connect it to my headphones.
Okay. Chitesh, why is the particle C having the maximum energy?
Sir.
Hmm.
Sir, the particle is in direct contact with the atmosphere.
It is not about direct contact with the atmosphere. There is something else. I spoke in terms of cohesive and adhesive forces. You at least remember those two terms of cohesive and adhesive forces. So what do you mean by cohesive force?
Attractive force. I mean, yeah, attractive force.
If there is a molecular attraction taking place between
the surface and the liquid.
Surface and liquid. Anybody else who can give me a better answer? Rohit, can you? No? Kirtana? I told this. Amrisha, can you?
In the between the same substance.
Yes. If there is a force of attraction taking place between the particles of the same substance, you call it to be Cohesive force.
Cohesive
If it is
force.
taking place between different substances, you call it to be adhesive force, right? So what happens here is, if you look at the molecular attraction that is taking place, particle A is experiencing the molecular attraction from the surrounding particles of equal value. You're able to see there is a sphere around it that is called a sphere of influence. Whereas for particle B, what is happening? Major part of it is experiencing the force from the downward particle. You're able to see some portion is outside. Some portion is outside, whereas the other portion is inside. What happens to this one? Half of the portion is inside and half of the portion is experiencing a complete force in the downward direction because there is no counterpart on the top for it to experience a force. There is no other particle at the top which is trying to pull the particle C. So major force it is experiencing is in the downward direction, as a result of which what is going to happen? It will have more force acting on it and it will have more energy associated with it. And that is what is a molecular theory of surface tension. So you tell me, out of the three particles A, B, and C, which one is at the surface? So A is obviously inside. What about B? B is closer to the surface, but C is the one which is at the top of the surface. So that is why the particles on the surface, right, they have more energy. So that's why I'm trying to relate it to the concept of something called as surface energy. This is very, very important. Listen to this carefully. Now, what will happen is, due to the surface tension, the film will start moving to the left. So what we are trying to do is, we are trying to balance it by applying a force in the opposite direction, which is slightly greater than the effect caused by the surface tension, so that I'm able to move the thread from AB to A dash B dash. When I do that, am I doing some work on it? Because I told you throughout science, right, wherever energy comes, what should our mind think of? We need not think anything outside the box. Wherever you see energy, there is something that is fixed. It is
Work done.
work done. So for us to calculate work done, what do we need? There are two parameters that are required. What are they? One is force and one is displacement. Right? If I am able to find out those two answers, I'll be able to calculate the force. That's the logic, right? So here, if you see, surface tension is actually not the force. Though the word tension comes, right? We have a misconception that surface tension means it is force. No. So surface tension is the amount of force that is acting per unit length. It has a completely different unit. It is Newton per meter, right? So if surface tension is equal to F by L, then what can I call that external force F as? F will be equal to T into L. Am I right? T into L, right? But if you observe, instead of T, right, they wrote sigma here. Don't get confused. Instead of T, they wrote sigma. But I wrote it as T into L, but they wrote it as 2T into L. So this is the point I was trying to stress upon. Listen to this carefully. Why did the 2 come? Because see, you need to answer this question for you to understand two other important concepts we'll be discussing today. That is called as excess pressure inside a soap bubble and liquid water. Sorry, excess pressure inside a liquid drop and soap bubble. Okay, listen to this carefully. The reason for the 2 is because of something called as free surface. Okay, what is it called as? What did I say? It's called as free surface, right? While I gave you the definition of surface tension, I told you what a free surface means. What does a free surface mean? Free surface basically means the surface which is exposed to air. Am I clear with that? So wherever you see this word free surface, going forward, if I use this word of free surface, right, you need to understand the fact that I'm trying to talk about the surface or the boundary that is directly exposed to air. Is that point getting registered in your mind? Now my question is, if you have to speak about the number of surface tensions that come into picture, it is dependent on the number of free surfaces that are present. So number of free surfaces will be equal to the number of surface tensions you need to write. So that is why they didn't write it as T into L. They wrote it as 2T into L, because Listen to this carefully. These two concepts are going to be throughout your chapter. If I take water in a glass, okay, let's assume there is a transparent glass in which I've taken water. The surface of the water is exposed to air on how many sides? One. It is one side. So if somebody asks you, how many free surfaces does a liquid have? Or water, see, for that matter, if it is water, petrol, kerosene, anything of that sort, it is a liquid. So for a liquid, what is going to happen? Below the surface, you have the liquid. Above the surface, you have air. So that liquid surface will have how many free surfaces? The surface of one free surface. Whereas when you talk about a soap bubble, what is there inside a soap bubble?
Air.
What is there outside the soap bubble? That is also air. So how many free surfaces does it have? Two. That is the reason why here, though you write it as F is equal to surface tension into length, you should not write one surface tension. You should write two surface tensions and then into L, because what is a film that is considered taken inside that frame? It is a soap film. So soap film basically has two free surfaces. Is a point getting registered in your mind? Right? This is a very, very important thing. Okay. You need to have this in your mind. A soap film has two free surfaces. Right. Now, what does this surface energy mean? Let's try to understand. From the name itself, it is clear. Surface is related to some object on the surface. Energy is related to the amount of work that we need to do to achieve something. So when I say surface energy, right, it is the energy possessed by the molecules of the surface film. Right? It is the energy possessed by the molecules of surface film. Okay, surface film is there, but what area should I consider? I should consider unit area. Okay, so energy possessed by molecules of surface film of unit area compared to, so energy of the particles on the surface compared to the energy possessed by the molecules which are in the interior part of that liquid is what is called as surface energy. That is the definition. Am I clear with that? So can you all first make a note of the first sentence alone? Don't write completely. First sentence alone, write it down. While writing, please concentrate. What are they saying? Energy possessed by the molecules of surface film of unit area compared to the molecules in the interior is called surface energy. So make a note of it. Are you done with that? Okay, are you done writing it?
Yes, sir.
Yes. Now the question is, but I always tell you one thing, that whenever you speak about energy, we should always speak in terms of work done. So here, when you applied a force, right, look at the activity that was done. You applied the force to do what? Did you try to decrease the surface area or increase the surface area? When the thread moves from AB to A dash B dash, is there an increase in the surface area of the rectangle or decrease in the surface area of the rectangle?
Increase.
So why are we doing that work? To increase the surface area. So what does surface tension do? Surface tension will decrease the surface area. We as opposing force of surface tension will try to increase the surface area. Makes sense? Now, having said that, you can say that the mathematical definition of surface energy is going to be this. It is equal to the work done in increasing the area of the surface film by unit amount. It is equal to the work done in increasing the area of the surface film by unit amount. Okay. Are you clear with that? Right. So mathematically, how I will write is, for surface energy, I'm calling it as SE. Surface energy is the amount of work done by the increase in area, delta A. So just because we use energy, we should not write work done. It is a work done per unit area. Am I clear with that point? So what is going to be the SI unit of it? It is going to be joule per meter square. It is going to be joule per meter square. Those whose videos are switched off, switch it on, please.
So if I switch it on, there is a net interruption.
What is there?
Like it's getting stuck. So like internet is getting used for like turning on my camera. So
Hmm.
I'm not able to turn it on.
But when I call you, at least you should respond. If you
Yeah,
don't,
yeah, sir.
So surface energy is equal to joule per meter square. Am I clear with that? So are these two basics in your mind, strong in your mind? Surface tension is amount of force per unit length, and surface energy is amount of work done per increasing the surface area. Right. Now, having said this, we will see the next important topic, that is the mathematical relation between surface energy and surface tension. This is the first derivation with respect to surface energy and surface tension. So I'm going to take the same diagram. So from A to B to A dash B dash, there is a displacement of X, and the length of this thread is going to be L, and there is tension acting in this direction. Now this will be 2T into L. Am I right? So what do I need to do? I need to calculate. See, for me to calculate surface energy, what are all the parameters I need? Mathematically, what does it say? I need work done in the numerator, delta A in the denominator. Am I right? So surface energy is equal to work done per unit area. So for me to calculate work done, what is the formula I'm going to use? Work done is equal to force into displacement. So what is the force with which we are actually pulling the thread? I wrote it there. I'm not able to hear you.
2TL, sir.
Yes. So force is 2TL into what is the displacement caused by that force? It's there in the diagram.
X.
X. Okay. Now, due to this, what is the increase in surface area of the free surface? So when I say increase in area, don't say L into X. How many free surfaces are there? 2 free surfaces. So for 2 free surfaces, what will be the change in area? It will be 2L into X. Am I right? So if I divide both, can I say surface energy is equal to 2T into L into X divided by 2 into L into X? So 2 and 2 are obviously gone. Lx and Lx are gone. So what is that I'm getting? I am saying that numerically, surface energy and surface tension have the same values. So there's a very, very important point to be noted. So numerically, surface tension and surface energy have the same value. They both are mathematically or numerically the same values. Am I clear with this? Shall I proceed? Listen, now. So experimental verification is not included. So problems, we'll do it later. Now the next concept that we'll see is pressure difference across curved surface. Now we need to apply all the concepts. So remember one thing, I'm going to discuss mostly only about cohesive force and the adhesive force. That point has to be strongly registered in your mind for you to understand the subsequent topics. Okay. Now the question is pressure difference across a curved liquid surface. Okay. Generally, when you take a liquid, right? Let's assume water itself. Water taken in a glass itself is there. Okay. When you take water in a glass tumbler or a glass material or a beaker, whatever you call it. Now, when we look at it, right, how does it actually look to our eyes? It looks flat, right? Does it look flat? Right. But you know what will happen at the edges? If you observe with a microscope, what is it you will be able to see? That there will be a small curvature. Okay, there will be a small curvature taking place. That curvature is taking place because of a parameter called as adhesive force and the cohesive force. So what is happening in this case is, generally, when you take water in some material, let's say glass itself, and you pour the water outside. Now tell me one thing, is that beaker going to be completely dry? What will you see inside? You can see some water drops stuck to that beaker. Yes or no? Am I clear with that? So there will be some water drops that are stuck to the beaker, and it is happening because what force is greater? The water particle is getting stuck to another material. So the force of attraction between two different materials is called as
Adhesive force.
So here adhesive force is greater than the cohesive force. Okay, don't write anything. I'll tell you when you're there is a separate lecture on that, which is called as angle of contact. I'll come to that. But what I'm trying to say is the same context is applicable everywhere. Okay. Now, when you see the pressure difference across a curved liquid surface, right? When you take the surface of the liquid, if you say it is flat, then the pressure exerted by the air and the pressure exerted by the liquid, they both will be of same value. Make sense? See, if something has to be flat, then the pressure on both the sides is supposed to be same. If suppose something is bent like this, which side the pressure is more, bottom or the top? See, it is like this. If I want to make this bend, I'm applying a force in this direction. It is getting bent like this. So which side pressure is more? The bottom or the top side? You think logically, if you want to, you're applying a force, it is getting bent like this. So you're pushing it outwards. So which side pressure is more? Well, if I have to show this diagram and explain, look at the second diagram, option B. Which side pressure is more, pink side or the white side?
Pink side.
That's right. That is what is supposed to happen, right? Okay. In a similar way, if something is bent in this form, U shape, so wherever you have that U shape, right? The side which has the U shape will have more pressure. That's the logic. Am I clear with that? Right. So why I'm telling you this point is, if you take a liquid drop, it is assumed to be a sphere. So for it to have a spherical shape, it takes a curvature like this, right? So this is how a liquid drop is going to look like. Now tell me one thing, since it has a curvature, which side of this liquid drop is the pressure more? Is it inside or is it outside?
Inside.
Are you able to understand? So based on this simple understanding, there are two more topics that we are going to discuss, which is called as excess pressure inside a liquid drop and excess pressure inside a soap bubble. Okay. I'm assuming that you would have heard all these things in your school. Did you?
Yes, sir.
But you're able to get the logic now? Okay. So before that, let me write down this point. So this is liquid. Sorry, this is liquid. This is the vapor side. The exposed side is air or some other vapor. I'll call it as vapor. So can I say in case A, pressure of vapor is equal to the pressure of liquid? Can I say this? In the case A, pressure of vapor is greater than pressure of liquid. You tell me for what is the case B.
Pressure of vapor is lesser than pressure of
Correct.
liquid.
So pressure of vapor is less than the pressure of liquid. What about case C? You're correct. Tell me. So pressure of
So vapor is
Vapor?
more than pressure of liquid.
So from this, can I conclude the fact that pressure on the concave side is greater than the pressure on the convex side? Can I make this simple conclusion? So pressure on the concave side. So I told you, that U shape is coming. Pressure on the concave side is always greater than the pressure on the convex side. Am I clear with that point? Right. Now, the next topic we will see is excess pressure inside a liquid drop. So this is the heading. So now you already know the answer why this concept of excess pressure is coming. What do you mean by excess pressure? Which side is the pressure more in this case? If you take a liquid drop, pink is the liquid, outside portion is vapor. So which side is the pressure greater? Just now we concluded
Pink.
inside. So what do you mean by excess pressure? It is the inside pressure minus the outside pressure. So we are saying the liquid is actually getting its shape of that spherical portion because there is an excess pressure inside the liquid drop. Am I clear with that point? Okay. Now what is our job is to calculate that value. Okay. Shall we try? Shall we calculate it? Yes or no? Yes. Listen to that carefully. So you're able to see, I'll show you this diagram. You're able to see a liquid drop. Let us say due to the excess pressure inside, the liquid drop is slightly getting expanded, very, very slightly. Okay. There is a slight expansion of that liquid drop where its radius is changing from R to R plus dr. That pink color portion that is there outside, no, the dotted lines. The dotted lines is the new radius, that is the new spherical surface that is being formed. Okay. Now tell me one thing. Now I'm going to ask you a sequence of questions. See, who's doing this work, right? Who is doing this work to increase the area?
Pressure.
It's the pressure, right? So if I'm able to calculate the work done, right? If I'm able to calculate the work done by pressure, then what is a mathematical equation I'm supposed to write? What is the mathematical equation I'm supposed to write? Pressure is equal to, work done is equal to force into displacement. Can I write it like this? But what is the force that is acting inside? Force, how will you write it in terms of pressure and area?
PA.
P into A. So pressure inside is small p. That is the excess pressure. That small p is actually liquid pressure minus vapor pressure. That should be in your mind. So small p is the excess pressure. So excess pressure multiplied with what is the area on which that excess pressure is actually acting? Is it not 4 pi r square because it's spherical? For a sphere, the area is 4 pi r square into dr. Make sense? So I'll call this as equation number 1. I'll call this as equation number 1. But Can I write work done is equal to surface energy into increase in area? Just now we saw surface energy is work done per unit area or increase in area. So work done will be equal to surface energy into increase in area. But we know that surface energy is numerically equal to what?
Tension.
What tension?
Surface tension.
Yes, it is equal to surface tension. So can I replace it with T? But I need to be very careful here. Okay, I need to be very careful. Listen to this carefully. What is a drop you are using? You're using liquid drop. For a liquid drop, how many free surfaces are there?
1.
So how many surface tension should I write?
1.
I wrote T. Into what is the change in area that is taking place? What is the change in area that is taking place? It is 4 pi into r plus dr the whole square minus 4 pi r square. I'm actually calculating the increase in that area. Means this area is what I'm calculating. I marked with yellow. Are you able to see that? Right. So T into, I'll take that 4 pi outside. Can I write it as r plus dr the whole square minus r square? So it is 4 pi t into, what is r plus dr the whole square? It is r square plus dr the whole square plus 2 times r dr minus r square. Can I say that?
Yes, sir.
Yes. 1 minute. Now, this r square and r square get cancelled. So I'll have 4 pi t into, see, dr is a very, very, very small quantity. The dr square can be approximated to 0. So 4 pi t into, it is going to be 2r dr. Can I call this as 2? Now tell me one thing. What is expression number 1? It is pi into 4 pi r square dr, but that value is nothing but work done. And second expression 4 pi t into 2r dr is also work done. So from 1 and 2, can I say that they both are same?
Yes, sir.
When they both are same, can I say p into 4 pi r square dr is equal to 4 into 2 is 8. Can I write it as 8 pi t into r dr? So you tell me what will get cancelled. Dr and dr are gone. 1 r will cancel this. This 4 pi will cancel this 8 pi 2 times. So excess pressure will be equal to 2 into T is there on the right hand side. There is 1 R left here, which will go to the denominator and it will be 2T divided by R. So the excess pressure inside is equal to 2T divided by R. Am I clear?
Yes, sir.
So if this derivation is asked, okay, what are they asking? They are asking the excess pressure inside a liquid drop, which is equal to 2 into capital T divided by R. Okay. Shall I proceed to the next one? Right. See, the next topic is excess pressure inside a soap bubble. Okay, this is a very good practice for you. The diagram, every step is same. Every step is same, but there is only one difference that is going to be there. Can someone tell me which step, which point will change?
2 surface tensions because of 2 surface.
That's it. So what is the only place thing will change? Instead of 1T here, I need to put 2T.
2.
So when I put that, what will the excess pressure come out to be? If in the case of liquid drop, it is 2T by R, there it will come out as?
4T by R.
That's it. Okay. So can you all just quickly write it down? You yourself can derive and see. I want you to practice immediately. Can you do that, please? Are you all done? So you're able to write it on your own? Let me know if you're done.
Done, sir.
Done? Good. So you got that 40 by R. So it's the same thing. What are the steps we need to follow? First, write the expression for work done. Work done is equal to surface energy into increase in area. Then again, you'll write work done is equal to force into displacement. And then you have to equate both. Next. So the next part of the chapter is something called as angle of contact. So there is also another important concept, okay? So from this, we'll be discussing something called as capillarity and capillary action. Okay, now listen to this carefully. Now, I gave you an example of that water and the glass, right? When you take water in a glass, you pour it out, you will be able to see some liquid drops stuck to that glass. It is happening because adhesive force is greater than the cohesive force, right? So if there is any liquid which has this property where the adhesive force is greater than the cohesive force, then that liquid will have the tendency to wet the solid surface. So liquid has a tendency to wet the solid surface, and it will have the surface will have a shape which is going to be called as concave meniscus. It's called as concave meniscus. For example, the option A that is there. If you look at it, right, when you take water and pour it into a glass vessel, actually you will see a shape of this sort. Why is it happening? Because the adhesive force is greater than the cohesive force. Okay. Next, if the adhesive force is less than the cohesive force, then the liquid does not wet the solid. For example, you take mercury and you pour it into a glass vessel. You take out the mercury, right, from inside. What will happen is the glass will not have any particles of mercury stuck to it, right? Meaning the liquid, the mercury is there, no, it does not wet the solid, and that kind of a liquid will form a meniscus called as convex meniscus. Make sense? So it will have a shape like this. So the diagram is with option B. So what is the third possibility? The one is greater. The third one is equal to. If adhesive force is equal to cohesive force, then the liquid surface will be plane. Okay, that generally happens when you take pure water, that is distilled water in silver vessel. Am I clear with that? No impurities in it. Right? By all these three things happening, right, I want you to focus on one important angle or what it is. You're able to see that if I draw a tangent at this point to that curve, if I draw a tangent at that point, the tangent is making an angle with the solid surface. Am I right? See, I repeat it. For that curved surface, if I draw a tangent at the point of contact, where that liquid is in contact with the solid, if I draw a tangent, then the tangent is making an angle with respect to the solid surface itself. And that angle is what is called as angle of contact. That is what is called as the angle of contact. Now the next question is, if I see for the convex meniscus, if I draw a tangent like this, I'll be able to define an angle in this way. I'll be able to define an angle in this way. Right. That is also called as angle of contact. Whereas for the third case, where you have a plane surface, there also you have angle of contact. So in the third case, it is obvious that the angle of contact is exactly equal to 90 degrees. Make sense? Now we need to give a definition to this. So what is this angle of contact? It is defined as the angle theta between whom? Between the tangent drawn to the liquid surface at the point of contact and the solid surface that is inside the liquid. Because you can ask me a question, sir, when you're saying solid surface, why are we not taking this angle and calling it as angle of contact? No, this is not called as angle of contact according to definition. So how is the angle of contact defined as? It is the tangent drawn between, so it is angle between the tangent drawn to the liquid surface at the point of contact and the solid surface inside the liquid. Makes sense? Right. That is called as angle of contact. Right. Now, if you're clear, if you have written everything, I want you to underline the point solid surface inside the liquid. Please underline that. Solid surface inside the liquid. Now, shall we proceed? Let's try to understand. See. Now, the next question is shape of liquid meniscus in a narrow tube. So, when I take a narrow tube means if I want you to imagine a straw. Let's say you order for a fruit juice or something, they'll give you a straw, right? That straw which you're going to dip can be treated like a narrow tube. What happens generally when you dip that straw into the juice? What happens? The liquid starts getting raised, right? But in this context, we are not going to discuss about why the liquid is getting raised. That we will see later. You're only going to understand how can this angle of contact be related to the different forces that are existing in the system. Okay. Now listen to that carefully. Shape of liquid meniscus in a narrow tube. That is a heading. So when I talk about the shape of a liquid meniscus in narrow tube, now see. This diagram is there. At this point, my interest of study is only at point O. So if you observe at point O, what is happening? I am able to draw a tangent here, right? This tangent creates, or I'll give it a name called as surface tension of liquid and the vapor surface. It is a surface tension of the liquid and the vapor surface. So are you okay if I change it to T? I'll change it as T. You don't draw everything, okay? I'll tell you how you're supposed to draw. So the first tangent, the yellow color tangent that I draw on is named as surface tension T. And what is the subscript we are using? LV. What does LV stand for? It stands for liquid vapor pressure. Surface. Make sense? Next. I can draw a tangent here. And this tangent has a name as TSL. Means solid, and liquid. SL stands for solid liquid surface. Right. So I'm able to draw a third tangent. I use another color. Observe. I'm able to draw a third tangent, which we will call it as TSV. It's called as TSV. Okay, which is called as the surface tension of the solid and vapor surface. And the last force that we will take into consideration is FA, which is called as the adhesive force. is called as the adhesive force. Right. Now, obviously, the angle between TLV and TSV is what is called as theta, and that is what is called as the angle of contact. Is there any doubt from the diagram?
No, sir.
Now, listen to this carefully. If I say the point O is like this, the point O is like this. This is TLV. This is TSL. And this is the adhesive force. And this is the value of TSV. And if I take this to be theta. Okay. If I take this to be theta, then which is the vector which can be divided into two components, perpendicular components? Can you tell me? Which is not confined to X or Y direction. There is only one force I'm able to see. It is TLV. So the TLV can be resolved into two components as TLV sine theta, and it is going to be TLV cos theta. Okay. Since this water droplet, that point O, is at equilibrium, can I conclude, or can I say that TLV sine theta is equal to FA and TSV is equal to TLV cos theta plus TSL? See, TSV is acting upwards. TSV is equal to downward forces are TLV cos theta plus TSL. Okay. So from this, can I say TSV minus TSL divided by TLV is equal to cos theta? Yes or no?
Yes, sir.
Now you tell me one thing. If I want theta to be less than 0, theta is less than 90 degrees. If I want the value of theta to be less than 90 degrees, right, then what should cos theta be? Cos theta should be positive. Am I right? If you substitute an acute angle in cos, then the value of cos is positive. Because between 0 to 90, we know that in the first quadrant, it is going to be a positive value. Yes or no?
Yes, sir.
Yes. So if cos theta is positive, can I say that TSV is greater than TSL? Because see, TSV minus TSL is cos theta. So if cos theta is positive, then TSV is greater than TSL. So TSV is greater than TSL, meaning if the surface tension between the surface and the vapor, if the surface tension upward is greater than the downward force, right, then you will say you have a concave meniscus. You have a concave meniscus. Make sense? Now you tell me, if theta is greater than 90 degrees, what will happen to cos theta? Cos theta will be less than 0, implies TSV
Concave
is,
is inward bent.
yes, TSV is less than TSL. And what kind of a meniscus will you get? What kind of a meniscus are you going to get? Is it going to be a
Convex.
convex? So it is going to be a convex meniscus. If theta is equal to 90 degrees, then cos theta will be equal to 0. Then it is going to be a plane surface. then it is going to be planar. The surface will be plane. I hope you will be able to answer this. If it comes in exam, will you be able to handle it?
Yes, sir.
Very good. Shall I proceed?
Yes, sir.
There are two small concepts that are left out. So I want you all to concentrate. Listen. First is we will learn something called as capillarity. Capillarity is a phenomenon, right? So before that, you need to understand what is a capillary tube. A tube of very fine bore in the sense that path. Okay. So a tube of very fine bore is what is called as a capillary tube. So as I told you, when you want to imagine a capillary tube, imagine the straw that you put into a juice. That's what is called as capillary tube. And the phenomenon, see, when you put that straw into the juice, right, what will happen is the liquid will start racing. It is happening naturally, right? You don't do anything. You just put the straw, liquid is racing. The phenomenon of see, that is happening because the juice contains water, and water has this property of wetting the solid surface. Whereas if you take the same straw and put it into if you take a glass straw and say you put it into mercury, right, what will happen is there will be a fall in the level of the liquid, like how the diagram shows. This is what happens in practical. Okay, in reality, this is what is supposed to happen. Okay. So this phenomenon of rise or fall of liquid inside a capillary tube is what is called as capillary action. It is what is called as a capillary action. Is this getting registered in your mind?
Yes, sir.
Good. Now what we will do is we will do a small derivation where there is a rise of liquid taking in a capillary tube, and that formula that we are going to derive is what is called as ascent formula. Okay, we will see that. So the heading is going to be rise of liquid in a capillary tube, which is called as ascent formula. Now, tell me one thing. You have a vessel which contains liquid, where it can form a concave manner, where it has a tendency to rise inside a capillary tube. That is why the heading is also rise of a liquid in a capillary tube. So you need to consider only those kind of liquids where the adhesive force is greater than the cohesive force. That's what we have done, right? Now, with respect to the liquid surface, can I say that inside the tube, there is a height h raise in the liquid column? Can I say that? Yes or no?
Yes, sir.
Yes, sir.
See, when this liquid has a tendency to get raised, if you look with a microscope, what shape is going to take? When you see from the top, will it take a concave meniscus shape or a convex meniscus shape? Obviously, concave meniscus. Now, for this concave meniscus being formed, we know that the pressure on the concave side is greater than the convex side. So, point A is the one which is exposed to the atmosphere. Let us call it as, let us say the pressure at that point as P A. Right. Now, What will be the pressure at point B? What will be the pressure at point B? Can I say that the pressure at point B, can I say that the pressure at point B is equal to pressure at point A minus 2T divided by R? I'll tell you why is it so. Because PA minus PB is equal to 2T by R. Am I right? I told you excess pressure means the greater pressure minus smaller pressure. So PA minus PB is 2T by R. So I'll take PB to the other side. This 2T by R to the left hand side. So PA minus 2T by R is equal to PB. But we know that the pressure at point A is nothing but the atmospheric pressure itself, because it is exposed to the atmosphere. As simple as that. Am I right? Is the first diagram justified? Are you able to understand?
Yes, sir.
Oh. Now I need to justify the second diagram. So what I'm going to do is we'll be using two concepts, because whenever there is a rise in liquid, we can think of variation of pressure with respect to depth. So we can use the formula rho g h. Okay, that h is there, so I can make use of that formula. I'll think of it. Second is there a possibility where we can bring in the concept of angle of contact and start applying trigonometry? Is what the next question is. So for that, what we will do is, if I take the liquid surface like this, right? If I take the liquid surface like this, it is going to be so small that you can consider it to be a part of a sphere, where the center of that meniscus is here. Okay. Now tell me one thing. I want you all to concentrate again. If I take this tangent, then this angle will be called as the angle of contact. Make sense?
Yes, sir.
If that is the angle of contact, then how much will this angle be? Then how much will this angle be? Is it not going to be 90 minus theta?
Yes, sir.
Right. And we know that the tangent and radius are perpendicular to each other. So when they are perpendicular to each other, out of 90, 90 minus theta is gone. And how much is the angle that is going to be present here? That will be theta. I hope that makes sense. It is theta. Now what I will do is, I'll say the radius of the capillary tube is small r and the radius of the meniscus is capital R. Okay. The radius of the capillary tube is small r and radius of the meniscus is capital R. Now tell me, what is the relation between capital R and small r? What is the relation between capital R and small r?
Cos.
So what is cos? Small r divided by capital R is equal to cos theta, which implies capital R is equal to R divided by cos theta. Let me call this as 1 and let me call this as 2. Now, can I say that the excess pressure, that is PB, sorry, can I say the excess pressure, that is PA minus PB, which is 2T by R, right? So this is the excess pressure. PA minus PB is equal to 2T by R, right? So 2T divided by, in the place of capital R, can I write it as small r divided by cos theta? So this is nothing but 2T cos theta divided by R. Let me call this as 3. Any doubt in this expression?
No, sir.
Now, one last step. Is it not because of this excess pressure? Is it not because of this excess pressure the liquid has got raised?
Yes, sir.
Right. So this is an important statement I'll write. Due to excess pressure, liquid rises in the tube to height h, right? Then what can we conclude at equilibrium? At equilibrium, can I say that this excess pressure, see Pa minus Pb, I'll call it as small p, okay? Can I say that this excess pressure is what is equal to rho gh? So if I take this as 4, I already know that the excess pressure is 2t cos theta by small r. And I also know that the excess pressure is rho gh. And my job is to calculate the height. So what I will do is I will write rho gh is equal to 2t divided by r into cos theta. From this, h is equal to 2t cos theta divided by r rho g. So it is going to be 2t cos theta divided by r rho g. So this is the height to which the liquid has got raised because of all these pressure things that are happening inside. So that is why the name of the topic is rise of liquid in a capillary tube, which is also called as ascent formula. Clear with this?
Yes, sir.
Very good. So write it down. Okay. So let me know once you're done copying. If there is any doubt, get it clarified. Okay. Right. Let me know once you're done copying. Are you done?
Yes, sir.
Everybody? Nivedita, Amrisha,
Yes, sir. Yes, sir.
Mrita, Eric, Ritika.
Yes, sir.
Okay. So with this, we are done with this chapter. Okay. So these are all the important derivations that are there. So today's class, whatever notes you have prepared is very, very important. Okay. So in the next class, I'll either start with the 11th chapter or I might be starting with the 14th chapter, that is simple harmonic motion. So that I'll tell you in the next class. Okay. But be prepared for the class and come. Shall I proceed? I mean, shall we wind up?
Yes, sir.
Yes, sir.
Okay. I'll see you
Thank
guys.
you, sir.
Thank you, sir.
Thank you, sir.
Those who are there for math, right? You start at 6:10.